Okay, now let us look at unblocking send and receive. So, I said if there is a big chunk of data and we do not want to just wait for the transfer to complete, and we need to, this is called overlapping computation with communication. So that I mean, so why CPU should be idle when data is being transferred? CPU is saying, well, what I am doing. Okay. So CPU can be given some work. So I will give simple examples. Okay. I would say in this course you avoid it, do not go for this part. Okay. Just well, you can use this send receive, but do not think of overlapping right now. Okay. You can use unblocking send receive, but no need to overlap in the first program. Okay, so this is the illustration. So in fact, this part of the diagram is exactly same as what I put in the last lecture. Same as blocking send receive, right? The data goes to buffer, buffer to interconnect, and interconnect to another buffer for receive, and then to a program. But the only difference is this arrow. So while the data is being, well, while this data is being transferred, okay, I can do some computation, or in fact till here. So this computation can go on. Okay, once the computation finished, you can do something else. Okay, only thing is you have to make sure that this data transfer does happen. It's not that I say, well, mera kaam ho gaya, I give the post office and I am done. System has to make sure that data has reached here. So there are ways to ascertain the data would have reached there, otherwise your program will not run, right. So computation and communication can be overlapped, but there are some barriers. There are some signals which can be used to say, well, yes, my data has reached. Okay, the signal you can use it later, you do not need to just wait for the signal when you are overlapping. So when I start a new job after this, I would say, well, I am just going to look at the signal, and only when signal is green, then I am going to go ahead. Okay. So that is what we need to keep in mind, and this signal is stored in request. This is an object. Request is what has all the information. Okay, so let us look at the syntax. So pretty simple, same, very similar to what we had. Syntax wise is only this capital I is the difference, capital I. Okay, I send. Okay, this is also called asynchronous send. Okay, so I is, well, I mean I send is what I is the difference. So buffer and destination and tag. So you create a variable where I am going to put my data, but then typically I do not send one object at a time. That is waste. Why is it a waste? Because one object will go through the interconnect, there is a buffer writing, all that is waste. It takes time, no? So you should send a packet. So you want to send to your friend some big document, you do not want to send page by page, just put it together in a big packet and send it. Okay, so that is what is done. So buffer will be big data, could be an array, basically an array for scientific computing. Okay. So these are no mobile please. So so buffer is here. So I put the buffer where it goes, destination and tag, and the receive is buffer, source where I am getting from, and tag. So simple, except that I is sitting in front, and that is telling you is non blocking. You can do other things if you like, you do not need to wait. And also because it can, the function already returned, it will never get into a deadlock. Okay, deadlock is avoided with non-blocking. But this word non-blocking is used for many things. In networking, non-blocking is used. That's also transferring data. No, I mean phone call, phone exchanges, file transfers. These are used. So this I send, I receive. So this I is capital. Return immediately even if the communication is not finished. Method returns request instance. It's an object, so it basically instance of an object. And so I want to wait. So the signal is wait. So if I put request wait, then it wait until the function is completed. Okay. So as I said, you want to make sure that job is done. You just put this command. Okay. So that's what we need to do. So we can overlap computation and communication with this. So this is a pretty good website, MPA4Pi. If you just do Google, that's what you will get, and it has detailed description of the functions. So we will just use the same example. By the way, a small I also works. Small I also works. I send, I receive. Okay. I think capital I used both, I believe. Okay. So it's pretty simple. So there are two processors, rank 0 and rank 1. 0 is typically called master node and 1 is worker. So I am sending number 1.0. Okay. So I store it somewhere. So data 0 to 1. This is my buffer. Okay. I think this code has a problem. There should be data is written here, no? So where is the buffer? Buffer should, this code is I think there is a problem. Anyway, there should be data as well. Anyway, so this is the data. I send it. I send. So this is a variable which is here, and destination. Tag is optional. We don't need to. And it always returns something, request. So REQ, I just use the variable name is REQ. And meanwhile, once data is being sent, I can update this data, this one, to 1.5. Now what is going by the, so what am I sending, 1 or 1.5? 1. Okay. So even if when I change it here, packet is already gone. So changing here is not going to affect the packet which is in the transit. So this sending is done, and immediately after that this 1.5 can be done. It is not going to wait for the packet to be received. And REQ wait means this rank 0 master node is going to wait until this send is complete. Okay. Now rank 1, this is a worker node. So it is going to receive this variable from source 0 and is going to store it here in data, and it returns this flag object actually which has many flags. I am using only wait, but there are some more signatures. So request is very basically is some kind of variable which is updated while the job is being done. Okay. So when it is complete, then wait will say green, no need to wait, go ahead. Oh, sorry, this is data is request dot wait. So this is the syntax, it is not here. Data is request dot wait. So it is going to write it here, data, and then I am printing the data. So request has the request dot wait returns data. Okay. Okay. So request dot wait is returning data, and I am printing that. So the output is given below. So when I do it, process 1 is receiving. So this is only print. So is receiving 1.0 what was sent. Okay. So I want the data, then I have to use request dot wait. So request dot wait in fact has the information or data also along with it. There I used I receive with this as well. So, we will see some examples. Okay. So, wait is important before starting a new work. Your data may be here, it is okay, you can receive the data in a buffer, but if you are starting something new and I have not got this number 1.0, then I will be in trouble. So, the buffer is here. So, buffer is should have been there. Okay. So, this tells you that buffer is required, but probably if you do not put it, Python is bit flexible, even if you do not put a variable it can proceed. Okay. So, this is another example where I am showing you how to overlap communication with computation. So, let us go through the code which is there in Colab. So, rank 1 is now sending the data, sending some random number. So, I create a random number, random, and I send it with capital I. Now, I put capital I. So, this is a random number and what type of data that is. So, it is MPI double, it is a double precision number, and where is it going? Is destination 0, is going to master node. Is okay? Is clear? Is going to the master node. That's one. Now, send is done. So, I send will return. That means, it is ready to do the next execution. So, next execution is I get a different number which is 5 times this random number. Okay. So, this is immediately executed after the return. A return is almost immediate. It basically puts the number in the buffer and says, well, I am done, come. It does not care about buffer is emptied or not. Then of course, it receives the number from master node by I receive, and here this is where is going to be is going to be using the same variable I run, and where is going to be storing that number. So, this is a buffer. Same buffer can be used for send and receive. Okay, you just going to put the number whatever it receives and request dot wait. So, this is going to make sure that I receive is complete. If I do not put that, then I receive need not be complete and I am going somewhere here. That is the problem. In fact, in Colab you see the functions. If I put lot of barriers, in fact, I put barrier is also another thing. I put a barrier here, com dot barrier. That will make sure that all these MPI calls are complete. So, this is a roadblock. Until you have finished all your work, you can't get out. All of them complete. So, all the trucks will come saying everybody is done, all set, then only the barrier will be opened. Okay. So, there are ways to synchronize. So, these are all for synchronization. Now, what does rank 0 do? Rank 0 receives first, and which packet is going to receive? This packet is going to receive first. It is going to come here, and the type must be the same, MPI double. If you do not give it, it runs, but for big data it is good to give the type. Allocation and all are required, so it is good to give the type. And it says where is it coming from? Source equal to 1, and request. So, this is the output. Okay. So, request dot wait. So, this will wait for this receive to be complete. Why should I wait? Because the next line is random number is multiplied by 2. If I do not wait, what is going to happen? Random number for rank 0. By the way, is this random number same as this random number? Yes or no? No, they are in two different processors. So, there are two different variables in the RAM. It could be the same your laptop, or it could be in different nodes. They are two different variables. Okay, and rank 1 cannot touch this random. These are secure variables. Okay, this is process. One process cannot touch the RAM of a variable of another process.
So, they are local variables.
They are local variables for that process. Well, not local, not in the sense of function, is owned by that process. Okay. So, I multiply this by 2, this is overlapping, this is also overlapping, and this overlap when I multiply is required that I need to wait. If I do not wait, I I will not be multiplying this number, I will multiply whatever was there in the beginning. In fact, there is a num there is something rand equal to random equal to something random. I initialize it. So, if you look at the code, that will be, you can set it to 0. Okay. So, the float MPI double. Okay. I need to declare is a float double. I multiply by 2, then I send this number which is being accepted here, this receive. So, both are sending, both are receiving, and there is some overlap of communication computation. So, you need to be careful so that you receive the data before you work on it. That is the rule. And the same code is running on both the process. Right now, it may look obvious, but when you start coding, you will miss it. So, you have to make sure that you understand same code is running. So, I need to make sure what rank 0 is doing, what rank 1 is doing. Okay, using tags. So, tags are used to contrast multiple messages sent by a sender to a specific processor. So, I send 2 packets. Imagine I am sending 2 variables, one is password and another one is username. Okay. So, I need to tag it, no, which one is username, and there is no way to tell. Well, you do not, by the way, the name of the variable is not transferred. This name of the variable is not coming here. This name could have been any name. So, when I send a number, I just send the number. I am not going any identifier with that number. So, I send 2 strings, and one is password and one is user ID. So, you can't say user ID can't be user ID. User ID is user ID. So, I need to put a tag. So, that is why I wrote. So, you put tag with that. Okay. So, this is a simple example. So, I am doing a blocking send. Okay. You can do an unblocking send as well, but that is there in Colab. So, I take this data 0 1, I send it, but I put a tag 10. Next, I create another variable data 0 to 1 sec is second. Okay. This it is a different string. I send again, but I put a different tag. It is going to same destination 1, tag 10 and tag 11. These are integers. Huh? This can be pretty long integers. And I am sending this data and this data. Print. Well, I just for my own satisfaction I am printing them. Rank 1 receives the data. So, same tag, you need to give the same tag. It is a programmer, no? This is well. First number I say tag 10, right? First tag. Second number I put as tag 11. And I receive as data and data 2, and I print them. By the way, I can switch the order. So, data 2 will be certainly, I know which is data 2, tag 11 is data 2. When I execute them, both are running, and it is possible that this is the blocking one. So, this one will be complete first and this is completed next, but it is unblocking, then this guy, this guy may be completed later than that. It is possible unblocking. That is why weight is important. No? MPU. So, let us see what happens. So, I run with 2 processors. I need to, because I am using 2 processors. So, sending from 0 to 1, the first one and second one, and receiving is from 0. So, data is tag 10, which is clear, is 0 to 1, and tag 11 is this. Okay. So, without tag it will be confusing, which is first data and which is second data. Okay. And often we need to know which was first and second, or which is what.